In the last few videos, we've been talking about integration of non-negative functions. That is, we were assuming that we had a space x, m, mu, so a measure space, and we consider functions from the set that went to the real numbers and were non-negative. So we were only considering functions for which the image was a non-negative number. We defined the integral of these functions and worked with a few conversions theorems that were going to be helpful to determine if a function was integrable or not. But we want to extend this definition to functions that can be negative or positive. So what we're going to do for this is, let's say that our function is something like this. So if this is 0, and let's say that this is a function f, so obviously f is not non-negative. What we're going to do is first check where this function is negative. And once we have these two sets, what we will do is just consider the reflection. So minus f in the places where this function is negative. And then also consider the places where the function is positive. And so by doing this, what we're saying is we define two functions, f plus and f minus. And the idea will be to write f as f plus, the places where the function is positive, minus f minus. And the idea is that these two functions are non-negative. So in this drawing, f plus is going to be 0, this yellow thing here where the function is positive, and 0 where the function is negative. And f minus is going to be, well, the reflection of where the function is negative and 0 where the function is positive. So here the function was negative, we reflect it, and then when it's positive, we continue with 0. This function then is going to be f minus. So now we can write f as f plus minus, because I have to reflect it back to the blue line, f minus. And the absolute value of f is just f plus f minus. Now here we are just considering functions that go to the real numbers. And we could do all this also for functions that are complex by dividing each of the real and imaginary parts in their positive and negative parts. And so we're going to say that a function is integrable if the integral of the modulus of that function is finite. One important property is the following. If we take the absolute value of the integral of f, this, well, we can just separate f in the positive and negative part, will give us just the sum of the integral of f plus minus the integral of f minus. But now this, we can just use the triangle inequality, the integral of f plus the integral of f minus. But this now is just the integral of f plus f minus, and this we said was the absolute value or modulus of f. So always what we have is that the absolute value of the integral is less than or equal to the integral of the absolute value or modulus. And now one notation that we usually use is L curviel 1 of the measure to denote all the functions that are integrable, that have finite integral, so for which the integral of the absolute value is finite. But let's see the following proposition. This proposition says that if we have two integral functions, then the integral of f is equal to the integral of g, integrating on any set that's measurable, if and only if the integral of the modulus of f minus g is 0. And this happens also if and only if f and g are equal almost everywhere. Now, why is this important? Well, what we're saying is, let's say that we have a function f, and let's suppose that this set here is some set A with measure 0. When a set has measure 0, my measure doesn't even know that it's there. So integrating on that set is meaningless. It doesn't affect the integral at all. So I can just take another function g that can be equal to f. Well, let's just say that that is equal. And in the measure 0 set, it can just take any other value. Something like this. Let's say that now this is g. Well, these two functions are equal almost everywhere, because they're different only on this set, and this set has measure 0. Well, this proposition says that then their integrals are also going to be equal. And so here, when we define this set, I didn't say anything about this space being a norm, because it would have made sense to talk about this space and say, well, the norm of f is just going to be the integral. But I can't do that because there are different functions that will have the same norm, because I can just redefine my function on a set where the measure is 0, and then I will have two different functions for which the integral of this abstraction is 0. But then this is not a norm. Well, and the answer to make it a norm is right here, almost everywhere. So what we can do is define an equivalence relation that is going to be f is related to g if and only if they are equal almost everywhere. And then just consider, we're going to define it L1 of mu is going to be the curvy L1, but we will take the coefficient with this equivalence relation. And so when we say that a function f is in L1, what we're saying is, well, this function is going to be a representant of all the functions that are equal to it almost everywhere. We are not going to use the notation of classes, because actually this set will have elements of this form. But we're just going to abuse the notation and drop these brackets. So we'll just take f, just a function in L1, when the integral is finite. But we have to always keep in mind this, that when I take a function in L1, what I'm actually doing is take one function that is just one representant of many other functions that are equal to it almost everywhere.